Today, we are exploring a dimension we all travel through, but only in one direction: time. As physical beings, we have complete freedom to move through the three dimensions of space. We can walk left or right, climb up or down, and step forward or backward at will. Yet when it comes to the fourth dimension, we have absolutely zero spatial control. We are inexorably dragged forward, carried continuously from the past, through the present, and into the future. This creates a grand paradox. The mathematical equations that govern our physical reality, from Isaac Newton's classical mechanics to Albert Einstein's general relativity and modern quantum mechanics, are perfectly symmetric with respect to time. At the microscopic level, the universe makes no distinction between past and future. The physical laws governing individual particles work exactly the same in reverse, raising a serious question about why our everyday reality feels so entirely different. The macroscopic reality we experience tells a drastically different story. A shattered glass does not spontaneously reassemble itself on a table. Heat flows continuously from a hot cup of coffee into a cold room, never the reverse. People age, stars burn out, and the physical universe expands. But if you were to zoom all the way in on a single electron interacting with a photon, that interaction could perfectly reverse itself without breaking a single law of physics. Bridging the divide between these time-symmetric laws and our irreversible macro-reality remains an active paradox, requiring a more unified understanding of how these different scales interact. The first physical distinction between past and future emerged during the 19th century, driven by the practical need to understand the efficiency of steam engines. Entropy is a mathematical measure of probability. It counts the number of microscopic configurations, or microstates, that can produce a single, observable macroscopic description. Austrian physicist Ludwig Boltzmann provided the mathematical framework that solved our paradox, bridging the behavior of reversible microscopic particles with our irreversible macroscopic reality. To see how this engine works, we can look at an isolated system, a box divided in half, with all its gas molecules confined to the left side. This is a highly specific, low-entropy state. When the barrier is removed, the molecules spread out. They don't spread because they know about the direction of time. They spread because there are trillions of times more ways for the particles to be distributed evenly across the whole box than clustered in one corner. It is mathematically possible for all those molecules to randomly bounce off each other and perfectly rebound back into the left half of the box. But the probability of that occurring is so vanishingly small, it would take longer than the current age of the universe to happen just once. Time's forward march is an emergent property. We experience time moving in one direction because macroscopic objects, containing trillions of particles, are statistically compelled to drift from less probable states to more probable ones. This cosmic drift of entropy also governs how we experience time internally, dictating why we only remember the past and never the future. According to Landauer's principle in information theory, forming a memory or erasing information requires a physical modification to the synapses in your brain. That physical process requires the dissipation of heat. Dissipating heat directly increases the total entropy of the universe. Human consciousness exists with a memory of the past precisely because the past had lower entropy. Physical records, like memories in a brain, fossils set in rock, or photographs on film, can only form as the universe marches steadily towards disorder. If the forward flow of time relies entirely on the universe moving from order to disorder, we run into a massive causal problem. Where did all that original order come from? For entropy to be increasing today, the universe must have begun in a state of extraordinarily low entropy at the Big Bang. This requirement is known as the past hypothesis, and it aligns the cosmological expansion of the universe with our thermodynamic arrow of time. Modern astronomical data proves this to be true. Measurements from satellites mapping the cosmic microwave background, the afterglow of the Big Bang, confirm that the early universe was a remarkably hot, dense, and uniformly smooth plasma. In a universe dominated by gravity, a perfectly smooth distribution of matter is actually a state of extremely low entropy. For gravitating matter, high entropy looks like a black hole. Physicist Roger Penrose calculated the probability of the universe beginning in this pristine, perfectly smooth state. The odds are 1 part in 10 to the power of 10 to the power of 123. The hard data verifies that our entire experience of reality and the forward momentum of time itself depends completely on the universe starting from a set of conditions that are statistically almost impossible. Science has successfully mapped how the arrow of time operates. It is driven by the relentless mathematics of probability and the second law of thermodynamics. Yet the ultimate why remains an open mystery. We still do not know why the cosmos was born in the exact low entropy state required to let time flow in the first place. The cutting edge of physics is currently utilizing quantum computer simulations and gravitational wave observatories to test the extreme limits of thermodynamics, hunting for a complete answer. Until they find it, we remain travelers caught in a statistical current, moving forward on the momentum of the universe's initial low entropy state.